So, and basically leave this off, turn this off when I want to put magnets on it. Is that correct?
These wires make it go a bit.
Oh, so take the wires off maybe. Oh, I get you. All right, fantastic. You two are the best. Thank you so much. All righty, thank you, Johnny. Thank you, Tom. Have a great day. So you may notice me and Johnny are very tired. It's Pride Day today, and we just ran a giant event. I am so tired. I played in our football team. We got owned. I was the captain of our football team. Every year we enter a football team into Pride Cup, and every year we lose every game, and this year was no different. Several of my students were there, and it was very funny because they kicked my ass. So that's that. Yes. So today, I'll move this over. I like having this as a thing to look at. Hang on. There we go. Alrighty. Cool. So, you're done with your first exam. Everyone did worse than I would have liked, but that's okay. I don't think the average was a pass.
Thank you.
Yes, I think the average was well below a pass. So, I'll compute the statistics and let you know. Okay, if you want to know, I will compute the statistics and let you know. This was just a quick, looking at it, okay? I don't know, I have thoughts, but whatever. Importantly, the exam is over now. I'm going to turn off these. Let's do some light control. Now, I also, really buggered my hip playing sport. So, you're going to have to forgive me. Oh, no, don't turn off. No. Hang on. Thank you. I appreciate you. How do I turn off these freaking lights? There we go. Lectern off. Yeah, that's right. Now you can see the screen again. You want it back on?
No, this one is...
That one on. Wait, you want that light on or off? Off. Is that better? Oh, spooky. All right. Bestie, can you close the door for us? I appreciate you. James? Ian. Oh.
Close enough.
Yeah, I agree. Close enough. Oh, that's even better. All right. So today is Mardi Gras tomorrow. I hope everyone's going to go. You don't have to go. Ian, what are you doing? Talking to friends? Bring him in here. 1 second. All right. We'll wait for Ian. Online besties, skip ahead 1 minute. Ian's talking to his friend. Welcome. Big shout out to everyone who played in our sports team yesterday. And by yesterday, I mean like an hour ago. I don't think it was anyone from this class, but in my sports team. Certainly people from this class played in teams against us. It was a full physics team. We had the physics department always runs a team, and we always get owned. And me and the director of teaching always play. Question?
What's the website for the...
Yeah?
No, I just forgot it.
Why? Nah, it's Ecopol. Are you shitting me? It's ecopol.au, and the code is physicsgang. Now, today we're doing some more stuff. What we got on our agenda today in the first half, we're doing capacitance again. We did capacitance before. We're going to talk about how you can connect capacitors in series, how you connect them in parallel, and then also a very funky question type involving dielectrics. Okay? A note on exams, because of course I go through all the questions that relate to a topic, right? The questions for this lecture are jank. They're weird. I hate them. All right? You have my condolences. I'm going to try my best. But I saw them and I was like, how in the absolute crap are you supposed to do these questions? I'm going to try my best. But before we get there, let's do some baseline learning. 2 capacitors. Now imagine that you take your 2 capacitors and you place them next to each other, and they both have a capacitance of C. So this is, if we were to connect them like this, that would be a connection in parallel, right? Now, if we connect them either with a wire or just kind of take the pieces of metal and touch them. So we had two capacitors, and we make them touch so that we've got one big metal plate on one side, and we've got one big metal plate on the other side, open pole. What do you think the total capacitance is? So the capacitance of this one was C. The capacitance of this one was also C. We had two capacitors, each of C, and we just brought them in so that they were touching, so that they were a big capacitor. What do we think? Again, if you forgot, it's echopole.au, and the code is physicsgang. And I forgot that I actually had echopole questions in this lecture. I thought I forgot them, but I actually did them. So nice work, me, for remembering. Well, yes, of course it's 2C. It's 2C. It's just a bigger capacitor now, right? And that's what happens. When you add capacitors in parallel, they just become a bigger capacitor. That's it. It's really easy. If you just question. Oh, this is in elect courses, 100%. Okay, if you're asking, so this will be in elect courses until we get to the part where I pour a dielectric inside a capacitor. No, literally. The question at the end of this lecture that I want to prepare you for is, I take a capacitor and I pour dielectric in there. What is the capacitance as a function of how much dielectric I put in? That's the question I'm going to try and get you to do. So no, we might not. This one's not got an integral on it. It's got no integral. How? Well, because, okay, if we did a function of time, we'd have to do an integral, but we're not going to. Anyway, this is the first point, right? A vital point. If two capacitors are placed in parallel, or 3, or 4, or 5, or 6, if you place them in parallel so that the positive side of one is the positive side of the other, it's just the bigger capacity. You just add them together. That's all. That's sleigh besties. But what do you think? What happens when you add them in series? All right? Now, we are going to build on some existing circuit knowledge. Okay? If we have two capacitors in series, right? The first thing that has to be true is they must have the same amount of charge. The reason for this is if there's not the same amount of charge on each of them, there would be a voltage along the wire. And we cannot have a voltage along the wire. Okay? And also, I'm not 100% certain that I put these two in the right order. It might be minus Q and Q, right? But whatever. The importance is both the capacitors have a charge of Q. Okay, and I promise you I'll double check if I got this the right way around or not, but because we absolute value everything in capacitors, I didn't bother, right? But importantly, right, these two capacitors have the same charge, and they have a voltage that would add up to this battery voltage. And we know this because of Kirchhoff's voltage law that we learn in elec, right? Where the total change in voltage over any closed circuit is 0. So any voltage gained here must be lost here and here. It's how we had resistors in series, if you remember. When we had a battery and two resistors, the total voltage drop across those two resistors had to be equal to the total voltage supplied by the battery. So what we know as a fact is, one, that the charges are the same on both of them, so Q is the same, right? And you, by the way, you don't need to remember this derivation, okay? You just need to remember the answer. But we know that they have the same charge on them, right? No? Yeah. No? Why? Why? Pen? Yeah. They have the same charge, otherwise there'd be a voltage along the wire. And there can't be a voltage along a wire. They can't because it's a conductor, right? It's illegal. But they also have to have their voltages add up. And if we use the definition of capacitance, which was C is equal to Q over V, and we invert that, so we get V equals Q over C, well, it's V1 is equal to Q1 over C1, V2 is equal to Q2 over C2. If you add them together, you get something like this. More specifically, you get the thing you actually have to remember. That the capacitance total of a series of capacitors in series add up like this, right? Like you would do resistors in parallel, okay, if you've done this before. 1 over the total capacitance. That's what CT is. This is the total capacitance. 1 over that is equal to 1 over the first capacitor plus 1 over the second capacitor. So how you compute it is you take 1 over all the capacitances, add them together, and then you invert that answer. Now what this means, by the way, yes, very correct. The capacitors always reduce capacitance when you add them in series. It's like how when you add resistors in parallel, they always reduce in voltage. Okay? So if you're adding 2 capacitors in series, you're making a worse capacitor. That's all you're doing. Whereas if you add them in parallel, you're making a bigger capacitor. And those two are just things you kind of have to keep in your back pocket. You have to know they add up that way. Okay? I don't have a back pocket because I'm wearing my sports gear. All right? I know, I wish I had a back pocket. That's fine. So, another thing you'll see commonly, another thing you will have to do, is you'll have to do combinations of capacitors. So like you'll have, for example, in this series, we have 3 capacitors, C1, C2, and C3, and they're all added in a weird shape, right? We've got C1 and C2 in parallel, and C3 in series with them both. So what you do is you merge capacitors in little increments. So the first thing we would do is we would take these 2 capacitors in parallel, and we would merge it into one capacitor. Right? So now we've got capacitor C3 in parallel with a capacitor that has capacitance C2 and C1. I'm so tired of saying the word capacitor. I feel like my throat's going to give out. And then we would add these 2 together. We go, well, 1 over the total capacitance is equal to 1 over C3 plus 1 over C1 plus C2. Right? And then you'd find, well, that means CT is equal to the inverse of 1 over C3 plus 1 over C1 plus C2. So that's specifically of that order. If we had parallel, parallel, series, parallel, whatever, right? The idea is that you take pairs of capacitors, or if you've got like 3 in parallel or something, you can do them all together. But you have groups of them in series that you can reduce, or you have groups of them in parallel that you can reduce, and you reduce them piece by piece by piece until you've only got 1 left. That's the idea anyway. That's the intent. So let's try and figure it out. Let's do a nice example together. What's the total capacitance of this capacitor? Now, I want you to guess right now. Just call out a number. What do you think? 1.5. 1.5. Okay. Maybe. 1.5 what? Farads. Millifarad. Oh, who knows? It's going to be a number similar to these numbers, maybe, right? Well, that's what I want you to know. By the time this course is up, I want you to be able to look at that and tell me, is it going to be lower than 100, bigger than 300, or in between the 2? In between the 2. You reckon in between, right? I probably reckon that too, but let's figure it out. Because when you're doing exam questions, if you came to my revision session on Tuesday, did everyone come to that? Yes. Yeah, good, all right. If you came to that, you'll notice I screw up all the time, but I'm pretty good at figuring out when I've screwed up. That's the way that I make it through exams, because I'm very good at realizing, oh, no. And that's because I'm very good at kind of having good expectations of what the answer should look like. Okay, that's my recommendation to you is get good at realizing when you've screwed up. In life, as well as in physics. Let's do this one together. So this one's 100. Okay, good. Try again. This one's 100. This one's 200. And this one's 300. So whoever said 1.5, that was a factor of several factors of 10 off, but it's going to be 1.5 times 10 to the something. So these 2 capacitors, when we add them together, they make a capacitor that is 300, right? Because 100 plus 200. So we can I didn't even click a button that time. Okay. I swear. Move over pride, it's time for wrath. So this one's now 300, and we've also got another capacitor that is 300. Right? We've got two capacitors of 300 capacitance now, and we have to add them together. So the total capacitance is going to be 1 over 300 plus 1 over 300. And that's equal to 1 over 2 over 300, which is 300 over 2, or 150 millifarads. So it was in between 100 and 300, right? I wouldn't have guessed 150. I mean, maybe I would have, I don't know, right? But it's good to kind of have an expectation on your answer. It's annoying because in parallel they get bigger and in series they get smaller, so you kind of don't know, which way. Alrighty. So, charging sets of capacitors. This is a more common question. Who's done the pre-lab for next week? No one. Who did the lab this week? Who did all of the optional integrals for the lab this week? Some of you. I'm so proud of you, right? If you did it, good on you. Did it help you in the exam? Actually, yeah? Great. I'm so happy. Yeah, you might get lucky. You might get that exact question in the exam, right? Same vibes? Good, good. I'm proud to see it. Happy to see it. Alrighty. Well, if you were to consider doing the pre-lab for this lab, you would encounter questions about charging capacitors, because that's really where it becomes interesting, because of course, capacitors we treat typically as stores of energy. And so we want to know what happens when I charge and discharge a capacitor. So let's take a look at this question. We have two capacitors, and let's say we charge them, okay? Then we disconnect one of them and discharge it and plug it back in. What voltage do they have? That is a very, very, very common type of question that you will see. Now, what I'm going to do is see if I actually put in a slide for us to do it. No, because I'm dumb. Oh, no, I did. Good, good. Good on me. I'm less stupid than I think sometimes. So here's the two rules that you remember. Whenever two capacitors are in parallel, they must always have the same voltage. They must always have the same voltage. And this means that the charge redistributes along the two capacitors so that they have the same voltage. Okay? So that means that whichever one has a bigger capacitance will have a bigger charge, right? Because they will redistribute. Because you essentially say, well, V is equal to Q over C, and V1 equals V2, so Q1 over C1 equals Q2 over C2, right? When they are in series, they must always have the same charge. Two capacitors in series always have the same charge, and the voltage on each capacitor will change to make this true. Okay? So if we have C equals Q over V, right? We rearrange to solve for Q. We now have Q is equal to CV, which means C1V1 equals C2V2, right? We use that equation now. So that's how you solve these problems, but you must separate all your variables into two cases. The case before and the case after the charge or the discharge happened. Okay? And I'm going to go through an example to show you what I mean. It's from the labs. If you haven't done the pre-lab yet, lucky you, I'm doing it with you now. Okay? POG or not. Let's take a look. What we've got is we have a capacitor C1 fully charged and then disconnected. It has a voltage of V. Then we connect C1 with C2 in parallel. What is the voltage across those two capacitors? They're in parallel. In fact, we're basically always doing this in parallel because parallel is way easier than series. So what we need to do is work out how much charge did the first capacitor get when it got charged, and then how does that redistribute when we plug two capacitors into it, okay? So we'll do this first part. Let's say, okay, in the charging stage, I don't know, man. I don't know this stage. In the charging stage, right? I know the other lecturer uses this place, they use their own laptop. Maybe I should start doing that, right? We have C1, we have C equals Q over V. I always write this down because I always forget which way it goes, right? C1, and we'll call it B for before. No, we won't call it B for before. C1, that was the computer saving me from making a mistake, is equal to the voltage of capacitor 1, which was called V. There was no 1, there was no 2. It was just the voltage it was charged to is called V, right? Over Q1. This is why I have to write this. Otherwise, I always get it the wrong way around, okay? Q1 before over V. Q1 before is the charge the capacitor had before we plug in the second one, okay? So this is the stage when it's charged. Now, after it's charged, we know the following facts. We know that C2 is equal to Q2 over V2, and we know that C1 is equal to Q1 over V1, but this Q1 is Q1 after. This is after I've plugged those two in together, right? So we'll say this is together. We also know a couple more things. We know that V2 equals V1, right? Because they're in parallel together. They have to have the same voltage. Not necessarily V, that original voltage. And we also know that Q2 plus Q1 equals Q1 before, right? The total charge we had at the start got redistributed between the two capacitors. And now that we have those two statements, now that we have all of these equations, we are being asked to find this voltage in terms of this voltage. Okay, that's what we're going to do. So from here, it's just algebra, right? From here, we just do algebraic substitutions. So let's make the substitution. I'm going to change my color. I'm going to ruin everything. No, I don't want to do that. Yeah, I managed to avoid breaking everything. We're going to go blue, just so I can, change it up a bit. We're going to say, well, Q1 before over voltage with no subscript, because that's the voltage it was originally charged at, is equal to Q1 over V1. And I know this because both of those are capacitors, right? That's all capacitance 1, right? And we know that V2 equals V1, so we may as well just try and solve for V2, right? Or solve for V1. It doesn't matter. Now we're going to take this and make a substitution. So we'll go, all right, well, Q2 plus Q1 all over V is equal to Q1 over V1. Okay? Sorry, Q1, yeah, that's correct. Q1 over V1. Okay. And so let's expand this out, right? We've got Q2 over V plus Q1 over V is equal to Q1 over V1. And now what we're going to do is we're going to substitute in our capacitances. All right? We're going to say, okay, Q1 equals C1 V1, and Q2 equals C2 V2. Right? Because we want an answer that has C1 in it, C2 in it, and V in it. That's what we're looking for. Right? We don't want no Q's. We don't want no Q's in there. So let's make those substitutions, and we're going to make the substitutions on this side. Well, actually, also on this side. Right? So we'll say, okay, C1 V1 over V plus C2 V2 over V is equal to C1 V1 over V1. And now we can cancel those V1s. So that's kind of useful. Bring this back up. So now we've got C1 is equal to C1 V1 over V2, plus C2 V2 over V, right? And V1 and V2 are the same, right? So we may as well equate them. Let's call it V1. So now we go, all right, C1 is equal to C1 V1 over V plus C2 V1 over V, right? And we're looking for V, so we'll rearrange everything. So this is going to be C1 is equal to, I'm sorry, this is taking so long, but you know, this is how it goes, right? Is equal to C1 V1 plus C2 V2 all over V. Yay. Now we can swap it around. Oh, sorry. V1. Yes, you're right. And so that's equal to, I really should have given myself more space, right? C1 plus C2 outside of V1 over V. And then we can finally make V1 the subject. Dang it. Where do I have space? I'm going to write it in the box. Okay. So we have this as true. It is only in terms that we want, right? I said C1 equals this, which I just wrote equals C1 on the side just to make it the same, right? We have our equation in terms we want. It's in terms of the capacitances, the voltage we're looking for, and the voltage we started with. So we just have to make it prettier, right? So what we're going to do is go, all right, well, C1 plus C2 V1 is equal to C1 V1. Oh, God, that was a much quicker way to have done that. Yeah. No, sorry. Is equal to this times V. Yeah. But I just realized a way faster way of having done that. I'm so stupid. All right. Anyway, we're going to get the same answer. And then we're looking for V1, so we'll just say, all right, well, V1 is equal to C1 V over C1 plus C2, right? Right? We're looking for V1. Yeah. Because we're looking for the voltage after we've plugged them both in together. Now let me show you the way easier way to have done that. Are you ready? I'll do it on the next page. Correct. That's what I should have done from the start. I'm such an idiot. Look at this. Q1 before equals Q1 plus Q2. So C1V is equal to C1V1 plus C2V2. It's the same thing. No, oh my God, I'm so dumb. All right. Far out. This is what I get for not doing it ahead of time, right? Okay, so that's way easier. Just equate the charges, right? And what I like about me screwing this up, no, well, I mean, one, yes, so you don't do it, but two, is that no matter what smooth brain method you use, as long as you use the correct physics, you get there. It's just that there was a way quicker way to do it. And I wrote these labs. Oh, God. I'm so stupid. Anyway, so then you do the same sort of thing for the other ones. Just do charge equating, etc. I won't waste our time on that / oh, God. That was so embarrassing. That was... Oh, God. Yeah, sure. You're gassing me up. Appreciate it. All right. God, that was funny. All right. So, this is the kind of jank problem I wanted to show you about. This is what I warned you about. Yay. Delete. All right. Go back. Good. So, this is a problem. This is the kind of problem that you will see in some form of important thing. Assessment, maybe. Or at least these are the ones that I found looking at them hard. Now, the thing is that clearly I'm a dumbass because it took me forever to just go, oh, well, charges are equal, right? So I'm trying to think, what was I even thinking? I think I did do charges are equal and I just took forever to actually equate them. But, you know, whatever, I'm stupid. Used the wrong way of the capacitance equation. What happens if you've got a capacitor that is slowly being filled with a dielectric? Okay? Now, when we have a capacitor without a dielectric, right, let's say a parallel plate capacitor, we know, because we remember from last lecture, that the capacitance of a dielectric with plate area A and separation distance D is A epsilon naught over D. And we would also know, if you added a dielectric to it, right, if you added a dielectric to it, you would get, kappa A epsilon naught over D, where kappa is the dielectric constant, right? Because remember, adding a dielectric to a capacitor literally just changes epsilon into epsilon naught. It's pretty chill. The problem is, what if the dielectric isn't completely filling the capacitor? What if it's only a little bit in there?
A changes.
Yeah, kinda. Honestly, what we do is we treat it as two capacitors in parallel, right? We treat it as two capacitors where, you're correct, A changes, right? The first capacitor is this. It's the plate area A1, and this one has plate area A2, where, of course, A1 plus A2 was equal to our total area, right? And so you treat them as parallel capacitors, one with the dielectric, one without the dielectric. And the trick is that the plate size of each capacitor is changing over time. And that's the problem, right? That is our problem to deal with. So there's a lot of examples in the practice quizzes that you might like to look at.
Can you make the first one with the kappa?
Yep.
Then as our normal.
Yep.
And then integrate the other one.
Oh, we don't have to do integrals. You don't have to do integrals for once in your life. You want to integrate?
You like to find the total.
No, you just add them together. But, well, okay, look. You'd have to do some sort of voltage integral to figure out the capacitance. The thing is, these questions are much easier if you remember the capacitance of the shape, right? So, for example, if you didn't remember that the capacitance of a parallel plate was A epsilon naught, or epsilon, depending on the dielectric medium, over D, then you'd be having a really troubled time. But if you did remember that, then you don't have to do anything, really.
What are the shapes we're going to get with the assessment? Like
What shapes will you get?
plate, cylinder, and
Plate or rectangle. They'll give you a weird rectangle maybe, but it's still a plate. Cylinder, sphere. Remember? Plate, cylinder, sphere. Does anyone remember? This is the example we're going to do. Does anyone remember the capacitance of a cylindrical capacitor of length L? So it's in our previous week's lecture notes. Anyone want to bring it up? No?
Concentric cylinders, capacitance 2 pi L epsilon naught over Ln b over A.
2 pi epsilon naught. What is it?
4 pi epsilon. Oh wait, no, that was concentric spheres. 2 pi L epsilon naught over Ln of b over A.
Ln of B over A,
Yes.
where A is the inner radius and B is the outer radius. Excellent. So in this case, it's 2 pi L epsilon naught for us, Ln R2 over R1. You're the goat. Thank you so much. Now, did you Google it?
No, I have it here in my notes.
Oh, hell yeah. Okay. Now, I want you to appreciate that in the doing of this question, if you remembered that, this question becomes nearly trivial because it's just two capacitors, right? If you did not remember that, this question, you can work it out. We did work it out together last week. Not last week, Wednesday. We worked it out together on Wednesday. But in an exam, that's tough. So my recommendation to you is to have in your back pocket the parallel plate, the parallel cylinder, and the concentric sphere, that's the lowest priority, capacitances. Or you could do the electric fields. Like, the more you remember about them, the better, okay? Because they keep showing up and it's the same ones. So luckily, this is the capacitance of one without a dielectric. This is no dielectric, or we'll call no die. And if we have a dielectric, what's the capacitance now? 2 pi L kappa epsilon naught over ln R2 over R1. What I want you to appreciate is that there is not much functional difficulty to these questions. Because the question we have here is you have a cylindrical capacitor, right? That picture at the top, that's the top-down picture, and then the picture on the bottom, that's the whole picture, right? That's it from the side. I couldn't figure out how to do transparencies, okay? So let's say you have an entire capacitor like this, and you start pouring in a liquid of some dielectric constant K, derive the capacitance of the capacitor as a function of the height of the liquid. It's not too bad. Okay? I'm going to rub out some of the doodad, and I'll start it for you. Okay? Why is this eraser so bad? Okay. So, what we do, and what you will be told to do in the question, so don't worry, is we'll divide it in 2 halves. Okay? We'll have the part filled with the dielectric that has a height of h. That's what I told us. Height of h. And the part without the dielectric that has a height of, what do you think? L minus h. Exactly correct. And so all the capacitance is it's the capacitance of a capacitor filled with a dielectric of length h. Oh. It didn't go to the next slide for once. That's rare, isn't it? Which is 2 pi h kappa epsilon naught over ln R2 over R1 plus 2 pi L minus h epsilon naught over ln R2 over R1. That's all. That's the total capacitance. The questions look difficult, but you just split them up as 2 capacitors, and they're not too bad. Question, Bestie? Yes. So the question was, what about a circular capacitor for, like cylindrical, spherical. That's the word you were thinking. Like, concentric sphere capacitor, where it's like if it's filling up, it wouldn't fill up in like a nice orderly shape, right? And that perhaps means it's not really good to make an assessment question on that. Maybe that, well, yeah, it would be really difficult to do a sphere filling because it doesn't fill in an orderly fashion, right? Tarek. We do. Yep. But that's all we're doing is pretending that they're 2 capacitors in parallel. Because they are like the metal of one capacitor and the metal of another capacitor, they're touching. So they are basically 2 capacitors in parallel. And all we're doing is separating them out as 2 capacitors so that we can put kappa in one of them and not have kappa in the other. And that's, now, the actual questions in the exam are more confusing than this. Okay? They're weirder, right? So basically, I have, imagine it started out, yes, this is dielectric constant. So, well, no, but more people have this question. So imagine it's hollow, right? This at capacitance, of constant kappa. And this one is normal, we'll say, right? And so we have 2 capacitors, and what's happening, the hard question will be, what if they tell you the flow rate of the dielectric, right? And there you got an integral maybe, right? If they tell you, they don't tell you the height of the dielectric, maybe they give you the volume of the dielectric. and you have to figure out the height from it, right? Because if they give you the volume, you have to figure out the size of that ring, and you have to figure out, okay, how much, right, dielectric, how much volume gives you how much height, right? The question I'm doing here is the easiest possible one of the ones that you'll be assessed on. But it is conceptually that simple. You chop it at the interface, you have one capacitor full of dielectric, you have one capacitor not full of dielectric, the total capacitance is those two added together. That's all you do. But yes, now it's time for a break slide. Because after this break, we're doing completely new content. Completely unrelated to what we're doing before. So we'll take a 10-minute break, and during this break, I will do dumb stuff with this thing. We get some water. If we have time, what I'll do is I'll just redo the derivations for the other parts of the pre-lab. Yeah. Yeah. Oh, I'm so sore. We played football today, and I'm so unfit.
How long are the games?
30 minutes apiece.
And how many games was it?
So I played 2.
Oh, okay.
I used to exercise more, but whenever I'm lecturing, I stop going to the gym because I don't have time. And
So true.
that's right. Because I work all day every weekend. So I work all day Saturday and all day Sunday on like lectures and stuff. This weekend is my last weekend writing lectures. I'm so happy to be done. Not that I'll miss all of you, obviously, but I'm so happy to like not have to do this part of my job.
Do you lecture at the Moses?
What?
Other than physics?
No, you know what? I lecture 4 years. 4 years, I wish. 4 weeks a year. Because I do so much administration for the school. For example, I'm in charge of all the labs. I'm in charge of all the students in the labs, the casuals, the staff. I train all of them. I roster all of them. I run the equity committee. Run the EDI committee, so I got this hat. Right? Because we just had our Pride Day barbecue. That actually popped off. By the way, guys, just thank you all to all who came. All 1 of you, 2 of you, whoever showed up. You rock. And then, I just have too much other jobs at the university.
Does that mean we get a different lecture second time?
Oh, yeah.
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 Oh, man.
No.
Wait, does this mean we're gonna have a new dad?
Sorry, what?
Does this mean we're gonna have a new dad?
Dad! God, I'm not that old, am I? Far out!
Stepdad.
I
Are you in physics getting divorced?
actually, I'm surprised I haven't made a divorce joke. I love making divorce jokes.
We really have to be a streamer.
We used to do streams. I will show you on YouTube. Okay, one time we'll be doing this live stream for a conference. By the way, I run some conferences. One, I hate Vera Fasson, that guy, because he really he dogged my conference, right? He was a keynote speaker at a conference I organized online, and then we had half an hour to an hour to show up early to prepare, and he showed up 1 minute before it was due to start, and he couldn't figure out how to share his screen.
Is that the LCT you don't like about?
Yes, that's it. No, there's other things, but I won't talk about them on record. So,
They don't have the mic on.
I'm loud enough. I checked the recordings last week on Wednesday when the mic wasn't working. I checked the recordings. You can still hear me. So yeah.
They don't have that thing on. Guys, the blue on
Guesses, but you can ask 4 marks.
When blue one see that?
We just I'm not in charge of any. But Kate Jackson is the one who actually runs it. I can't make any decisions. So you talk to Kate. But if you want, you get what you want. Oh, I'm also not right now. Okay? Because you need something else. You need some evidence. Okay? But you've got to talk to Kate. Because I can't make any decisions. Kate is my boss, so she's the one who makes decisions. Now I walk up and down. Oh, I'm so old.
Do you piss and you know, but it tells you?
What?
Do you piss and you know, but it tells you?
Used to work with tutoring agency. I worked at actually.
Oh my god.
Oh,
Because he is Australian.
he did his PhD here. He did his PhD at UCIT.
Oh my god.
Yeah, 100%.
Send him my regards.
I will. I don't know why I walk around as an exercise league. So bad. Oh, Hamlet, banging. Is that your favorite Shakespeare play?
Let me do it again. But this time in character. You can guess who I was.
Okay. I did a lot of things. was laser physics. So I worked on optical trapping. Yeah, yeah. Oh, diamond is really trappable. It's really odd.
Can you shoot lasers at your eyes?
Sorry?
Can you shoot lasers at your eyes?
Not anymore. Not anymore. Hang on. There's a thing happening.
You know in the first year labs, you know the bottom floor?
Yeah.
What are those research rooms for? Is that PhD?
What color area is it?
It's like the green.
Oh,
You know when you like walk, got like the physics up above and then you like walk in and you turn.
yeah, those are like research labs.
Yeah.
We all have, so PhD students all get their own desk in like the office spaces, and then most experimentalists have a lab. The lab I worked out of is on the lower ground floor, and it's a laser lab, so you can't look into it because it's all blacked out. Sorry?
It's boring except when the lasers are on.
I fall asleep in this so much.
Is that because you're sleep deprived or it's dark or both?
It's dark, and I'm snoozing. Because what would happen is my experiments, they would run for an hour, and I like figured out a way to just remote desktop do it because I'd set it all. I'd go in and I'd align it, I'd get everything ready, and then I'd just go back to my desk and I'd click start from remote desktop, and I'd just sit there and watch the kind of stuff go. It was good. All right, let me prepare a little. I was gonna prepare more today, and then I realized that
Are we moving on to the magnetism as well?
yes, we are.
And then the whole building next door.
What's this?
Yeah.
Anyone want to come play with this? You can.
I would love to.
All right. Okay. So what you must do is you must take the magnet, and you must not touch anything with the magnet, but you may put the magnet close to this do that. So.
Whoa.
Oh, yeah. Don't be so fast. What are you doing? Nice. If you break it, I'll laugh.
What's the
You'll know if I break it.
Don't. Whatever. If you break it, bad things will happen to you specifically.
Oh, so I feel like
Now flip it over.
what's the beam?
So like. Oh, fuck, I hate that movie.
What things did you say I couldn't touch with this?
Anything. Yeah. So like don't touch any of this shit. But please use the magnet and move it near the beam. And now you've had enough beam time. Give someone some beam.
That's a lot of. And then the whole.
Yes, it's a fuck ton of voltage, so do not touch this. Don't touch it. Don't touch it. If you want to, unless you want to star in your own electro boom video.
If you go on the what is it, Dharma test or something?
Yeah, exactly. You get Dharma board,
Yeah.
right?
That's so cool.
That's pretty fun.
You
That's
can
pretty fun.
see the sign.
Alright, let him do it. Oh, you gotta use two. Gangster. Alright, careful. Don't touch anything. If you touch anything, I will die.
What makes
What would happen
the
if you like touched it?
Sorry?
Like if you touch the magnet to your belt, would it break it?
It might stick to one of the pieces of metal and then short everything out and explode.
Is that his ear?
Let's go.
Wow, cool, gangster. Chilly high.
What makes the line on the?
Oh, it's just a fluorescent doodad.
That's so.
Oh, phosphorescent. Please, just strong hands, bestie. Here you go. You want? Here you go. What about your name? Jane or Sarah?
When when the guy in Berkeley says, "Wow, the only machine is
Really?
100 electrons."
What's your actual name? Oh, that's cool. Do you have a cool name? Oh, wow. See, shit works. Anyway, well now I'm so glad you asked, Sarah. What's going on? Yeah! It's time. It's time for learning. Don't worry, there'll be more time to play with the doodad later, okay? Alrighty, why the F did it do that? It's exciting. Was it exciting? Who knows? Where'd I put my swipe card? Here it is. Okay. So, it's magnet time, baby! Now, you might be thinking, Tom, am I doing integrals today? The answer is, for today only, just for you, no integrals today. Instead, cross product. Do I remember how to do the cross product? No. I wrote it down though. Question.
Is it the fun cross product or the not fun?
Is there a fun? It involves vector. Yeah. Oh, yeah, but we have to do the actual matrix version of a cross product today. You have my condolences. But I promise you next week, which I haven't written the slides for quite yet, but I will soon. I promise you, full of integrals. You're going to have such a field day. We're going to have different types of integrals. We're going to have circular path integrals. We'll have area integrals because we'll have Gauss's law again, but for magnetism. We're going to have Ampere's law, which involves circulating integrals. And we're going to have the Biot-Savart law, which involves integrating something with a cross product in it. I'm sure you're all thrilled and excited. I am not, because I have to write the lectures for it. And also, we're going to do the Hall effect and a bunch of other stuff. We're doing a lot of cool stuff. And honestly, the questions aren't that bad. They're just like, the formula looks terrible. But let's learn some stuff. We're doing magnets today. We're doing baby's first magnet today. So the question was, what the heck? Why did the magnet make this go? Right? And why did changing the polarity of the magnet change the way in which the... God, I'm like Hamlet's dad now, walking around with a limp. God. If I die, I need you to avenge me by getting a HT on the test, all right? All right. Magnetic fields. Somewhat. Now, here's the thing. If you go into second year, you're going to learn that we are making an absolute crazy generalization here. Because magnetic fields is not B, but for us it is. Okay? The magnetic fields, it's the magnetic version of an electric field. That's what it is. All right? It's anything you could do with an electric field, yeah, you can do the magnetic version of it. Magnetic flux, hell yeah. Magnetic Gauss's law, hell yeah. Don't worry, magnetic Gauss's law is the easier one. Okay? It's way easier. You don't have to worry. All right. Magnetic field is a region of influence that mediates the magnetic force. So it's just like any other frickin' field, right? Why do the magnets work with a distance between them, even when they're not touching? It is the... Someone labeled these wrong. These two ends are repelling. Whoops. Anyway, it is the power of magnet, right? They are not touching, lo and behold. This is the kind of stuff that get you executed 200 years ago, right? Ooh. Show this to a Victorian child to instantly kill them. I subscribe to a lot of like memes that would kill a Victorian child, etc. What, kill a Victorian child? I wouldn't put it past them, honestly. Michael Faraday. We're going to learn Faraday's law. A lot of blood on that law, maybe. Now, charges experience the electric force, and they are the things that made the electric force. So it figures that the things that create magnetic fields are the things that experience magnetic fields. And so those things are magnets, as we just saw, but magnets are boring. What's more interesting is that it is moving charges that experience magnetic fields. And if you ask me, Tom, what about relative velocity? The answer is never think that. Do not think about relative velocity here. We will not do relativistic electrodynamics. It is cursed. We are not touching it. Sorry? Third year. Yeah, you got heaps of time. It gets whack, all right? It gets way more whack than you think. Anyway, so the SI unit is the Tesla, named after that person. Tesla. It's got a T. This one always looks like a little helmet to me, right? It's like the Praise the Sun guy, if you remember Dark Souls. I just play too much Dark Souls. That's how I see it, right? Sorry? Yeah, it looks like Solier, the sun guy, right? Like Praise the Sun, you know? I have never played Dark Souls. I'm a poser. It's too hard. And that doesn't bode well considering I'm about to teach you some hard physics, but you should never give up, even if I did at Dark Souls, okay? Now, the first thing I need to say is, well, technically this is actually magnetic flux density, and magnetic field is given by M, I think, or H. No, M? I forget. The point is, it doesn't matter to us. It's the magnetic field right now. It was the magnetic field when we did it in high school, and it's the magnetic field this year. And then next year, when you realize it's not really the magnetic field, I want you to know I knew this, okay, and I told you, and I'm not deliberately deceiving you. I am deliberately deceiving you, but I'm only doing it because you're going to be assessed with the B field, and it would unnecessarily confuse you to talk about other fields. And also, I don't want to learn it, so I teach it to you, all right? So step one, magnetic field lines. They've got similar vibes to electric field lines. The direction of the arrow indicates the direction of force on a magnetic north pole. So for magnets, some people very smartly use plus and minus because they are two opposites. But some people, us, use north and south. All right? Now, when you point a compass, you know, it has a north pole and a south pole. Where does the north pole point on a compass? To the north pole. So the north pole points north. And therefore, at the north pole, what pole of a magnet is there? South. Very good. Because the north pole is magnetically south, and the south pole is magnetically north, because the north pole is named, or more specifically, the north end of a magnet is named because it points north. Therefore, the top end of the Earth is south, right? Whack! You don't need to know that. I just wanted to put that in there. Sorry? Is it? Oh, I get it. Sorry, hang on. Let me just... Oh, I'm too old. God. All right, anyway. Fuck. The direction of the arrow indicates the direction of force on a north magnetic pole. And that means the opposite direction is the direction of force on a south magnetic pole, right? But to find the direction of force on a moving charge, it is slightly, substantially more complicated. Now, the density of the lines indicates the relative strength. So the closer they are together, the stronger the fields. A question I want to think for all of you: why is it that a magnet can pick up metal using either end? Why both north and south poles of a magnet can pick up an object? Why is it attractive both ways? We will not go through it in this course. I just want you to think about it. There's a lot of cool things you can think about with magnets. Sometimes I like to just sit around and think about magnets. Now, unlike electric field lines, which makes dealing with magnets honestly way easier than electric fields, there's no such thing as a magnetic monopole. All magnets are dipoles, okay, or quadrupoles, but dipoles, all right? There's no such thing as this. You can't just have this radial magnetic fields, okay? And that means the Gauss's law for magnetism is really easy because the magnet enclosed is zero. It's always zero because you never have uneven magnetness, right? You can never have more of a north pole than you do of a south pole. It's just not possible. So, yay, go us. Exciting, all right? There's no magnetic monopoles. So here's the first thing that we have learned, that we must learn. I'm going to check. You know, we'll probably finish early again today. Oh, dang it. Okay, we'll finish early again today, and I will start the next lecture early if we finish early. And it's just because I want to, and I haven't even written the slides yet, so I'm literally going to vibe just some preparatory stuff because there's a lot next lecture. Okay, so the force on a charge, the simple version, every time I see that I think Taylor's version, right? This is the easy version. It's technically always Q, charge, V, the velocity, cross B, the magnetic field. But for simple cases, i.e. cases someone could draw, all right, it's QVB sine theta. Q the charge, V the velocity, not the voltage, B the magnetic field, and theta the angle between B and V. Okay? So what this means is that the magnetic field is maximized when the velocity is perpendicular to the magnetic field. When those two are perpendicular, we have a maximized force on our object. We call this the magnetic force. We sometimes call it the Lorentz force. Okay? And it's the simple version. To figure out the direction of force, though, it is a problem. So, when you have a charge moving in one direction and the magnetic field is in another direction, the actual direction of the velocity is in the third direction. So the actual direction of force is in the third direction. Because when you take two vectors, which B and V are, if you cross product vectors, the direction, because when you cross product two vectors, the result is another vector. That's the shittest thing about this, right? When we did dot product, it was lovely. You just take them, you put the cos between them, you're done, right? You get a scalar. But when you cross product two vectors, your reward is another vector. And that's why doing cross products is annoying and hard. And that means you need to figure out the direction of the vector. Now, you can do so using vector mathematics. We will do this later. But the simple way is to use the right-hand palm rule. I couldn't get a picture of a palm. So it's this physics gang side. This is literally the image I used on our Discord server. So, that's why I put it in here. Welcome, welcome. So, the direction of force has to be perpendicular to both the velocity, or more specifically, perpendicular to the component of velocity that is perpendicular to the magnetic field. So the velocity across the magnetic field. Perpendicular to that and perpendicular to the magnetic field. So the way I think about it is get your right hand. And it's got to be your right hand. So when you're doing your exam and you're writing with your right hand, put the pen down. You put your hand up, all right? If you use your left hand, you get it the wrong way. So, how many thumbs do you have? On your hand, on your right hand. How many thumbs? One. On average. The modal number is 1. Right. How many fingers? More than 1. Probably, statistically speaking. So when you do this, your thumb is the direction of the velocity because there is one charge and you have one thumb. Your fingers are the direction of the magnetic field because it has many field lines and you have many fingers, statistically speaking. And then your palm is the direction of the force. Okay? The force comes from the palm. So in this case, the force on this charge. Our fingers point down, right? And this is just basically me making you all go slay because it's Pride this month, right? That's my Mardi Gras trick. So the velocity is that way, right? Because the perpendicular component of velocity is off to the, is it left for you? Yes, left. For me, it's the right. So our fingers point down, our thumb points to the right, so you're mirroring what I'm doing. No, do that. Yeah, that's correct, that's correct. You're doing this. Don't do what I'm doing. No. So for you, it looks like this. For me, notice we face opposite directions. So when I do this, don't do this. You do this, but over this way, okay? Okay, you got it? You got it? Okay, so then, what's the direction of the palm? Out of the page, out of the page. So the direction of force on this charge is out of the page. Okay? What if it were a negative charge? You reverse it. Or you can use your left hand, slay, right? Left, because I don't know if you know this, but your left hand is a mirror of your right hand. Right? So you can use your left hand for negative particles, or you just use your right hand and you reverse it. Either one works. But yeah, so in the exam, I expect a lot of little dances. That's my favorite part about magnetism. You have to do a little dance. And no one does it in their head. No one remembers this stuff. You always have to use your head. It's the best part. Yes, that's what we'll do after this.
Is there like a question where we actually need to use our hands?
Yeah, there will be. There's a bunch of questions where you won't have to do like something simple like QVB sine theta, but you'll be given a diagram where you ask which way is the force on the charge, or something like that. Especially next week, we're going to do Hall effect, which is this thing that charges do, and we're going to be asked a question, which way do the charges accumulate, left or right? And so you do have to do it without, I know it's kind of, the good part about cross products is you don't have to think about it. You just do it, and it's like, that's the direction. It's this big schmozzle. Anyway, let's try this question. Charge is an electron. B equals 0.32, V equals 3, theta equals 60. What's the direction and magnitude of the force? Well, let's do the easy one. F is equal to QVB sine theta. Now, those of you who are on tour, you might not know, but we have a building here called the Queen Victoria Building. That's how I remember Queen Victoria Building, QVB. QVB, Queen Victoria Building. You gotta go visit. It's got a good pen store in this, where I buy my fountain pen inks. I love fountain pens. Anyway, I don't have any hobbies that aren't deliciously nerdy. What's the charge of an electron, everyone? All right, so I'm writing 1.602 because the negative indicates a reversal of the direction. If you are doing it with a vector cross product, you absolutely must include that negative to ensure the direction flips. For us, we're going to just flip the direction that we would say. Question?
If we say minus that and then say the direction's coming out of the page, is that still correct?
Sure. Negative out of the page means into the page. Yeah. I would say so. The problem is that you're getting answered by a computer. So you have to answer it how the computer expects you to answer it. Right? Unfortunately. Anyway, times 3 times 0.32 times sine of 60. What's that? It's something. Anyone want to calculate it for us? I didn't bring my calculator. I'm not doing it. Sarah, I remember your name, so you have to do it. Yep. 19 newtons. All right, and it's, hang on. It's into the page, right? Yeah, into the page. Because it's the opposite of what our hand would say. So, Tarek. Yeah. Okay, in the exam, when they give you questions, it'll be a drop-down menu to select the direction. So, you just click the one that says into the page or out of the page. Yes?
Let's say, for example, I write the loss in a vector format.
Yep.
Okay, just sine 60.
Yep.
And then find also Q in a vector format,
Yeah.
which is going to be just down.
You mean B in a vector format?
And B
Yeah.
as well.
Yeah.
And then
Then when you do the cross product, it'll only have a Z component, right? It'll only have an into out of the page component. And then you'll be like, well, that's it.
yeah, so that's
Yeah, that's how you do it. Exactly right. And we will take a look at it later.
In the exam, does it check whether you've got a minus and
It should. Don't know if it does, but it should. Well, basically, if you put the wrong direction, but you also put a minus, so you are technically correct, just email and say, look, give me mark. And we'll probably give you mark. You have to email me and Kate. Technically, email Kate. Kate's in charge, but I like to help. Anyway, what about the acceleration? So the force on this electron is nothing. What do we think the acceleration on the electron is? Small? No, it's insanely large. Watch this. F equals ma. Don't watch this. Watch the slide. Go to next slide. Yeah. Every time I'm trying to make a point. What's the charge on an electron? Well, sorry. F equals ma. Thanks. F equals ma, right? But where the A? I swear to God. We'll just wait. We'll just wait. We're just gonna wait for it. Just gonna. Yes. Okay, we did it. Calm, Tom. All right. So F equals ma, right? Which means that A equals F over m, which is 1.3 times 10 to the minus 19 divided by 9.109 times 10 to the minus frickin' 31. Okay? So that is an insanely high acceleration. Sorry? Probably. Well, I don't know. It looks to me like it'll be 10 to the 12-ish, right? Some big number. So just keep that in mind. If the force is small, the acceleration could be still large because electrons are little babies. Okay, Taylor's version. What if you have them in coordinate form? This is what you will more often see, right? And what I want you to be thinking when you see this is, it's me, hi, I'm the problem, it's me, because this is what the problem is, right? If they're expressed in coordinate form with I, J, and K notation, it's this. It's so cursed, right? You do it component by component. You do the X component, or the I component, as we could say. Then you do the Y component. Then you do the Z component. Oh, wait, I didn't mean to turn that off. Hang on. I can't computer. Yay. It's hard. So the problem is, you're going to have to do it in an exam, and you can't Google it. Question. What? Thank you. Thank you. Right? The only way I remember it, right, is I remember that the V always goes before the B, okay? In any given section, its own letter can never show up. So X is never in the X direction. There's no X component in this first part. There's no Y component in this second part. There's no Z component in this third part. And then I remember that it goes Y, X, Y, Z, X, right? The first one is always a Y, the second one's a Z, the third one's an X, and then you can kind of see that they have these weird pairs. So it's VY, BZ, VZ, BY, and so on and so on. You have to find some way of memorizing it. You can do the vector square if you want, right? Yeah, exactly. Do the matrix form, right, with IJK, VX, VY, VZ, BX, BY, BZ. But you must have some way of remembering how to do a cross product in an exam. I'm sorry, but it is necessary because you're going to get a question on it. Or at least there are many questions on it. So I would recommend committing to memory. What we can do is everyone can post in Discord their favorite mnemonic to remember a cross product. I'll level with you. I don't remember how to do it, but I don't have to do the exam. So there you go. Right? So let's try an example. We have this velocity vector, that magnetic field vector. What's the force? So let's label all these components first, okay? We've got Vx equals 0.25. Sorry? We could. I'm avoiding it because I just don't vibe with it. But you absolutely could. You could just write it as V equals 0.25, 0.750, right? If you like doing vectors, you gold. You just have a fun time, right? Basically, I teach for the people who hate doing stuff, like vectors. All right, now Vz equals 0. And then Bx equals 0. Good. By equals 1.02. And Bz, oh wow, that was a terrible B. Bz equals 2.03. Okay. Yes, that's correct. But let's just do the cross product first. We'll get the cross product out of the way first. Then we'll multiply in Q. But that is a very good point, right? You'd be tempted to do the cross product and then go, oh, I'm done. No. There's a Q in there, right? Don't you forget that. Anyway, now we do the big form. All right, so V cross B is equal to, so first of all, we're doing VYBZ, so that's 0.75 times 2.03, and then it's the opposite, so that's minus VZBY, which is 0, I think, right? Yep, 0 times whatever, I don't care. As soon as you see a 0, Screw it. Screw that next part. So that's in the I direction. In the J direction, we have Vz, it would be. Yes, Vz, 0. Don't care because it's, times Bx. Minus V, what was it? We had Z. I'm trying to remember. So it would be Vx, Bz. Yes, good. Okay, good. 0.25 times 2.03, right? Plus, now we start with Vx, 0.25 times By, which is 1.02, right? Cool. Minus Vy Bx, right? Which is 0. Good. That's in the J, this is in the K. So what I'd recommend doing is just, you can make your own ones, right? Just try, as what I'm doing, try doing it off the top of your head, and then go, yeah, okay, yeah, and eventually you'll get it. All right? Now we have to do the math. We should, but I'm doing the long way because it's like better for the whole lecturing thing. See, part of the problem in teaching is that, yeah, I want to take a lot of shortcuts, but, oh, come on! But one, the computer hates me. And two, it's important to go through things kind of the long and boring way because that's what matters. But yeah, okay, so, yeah, because you're right, we could just kind of neglect that 0.03, right? Say, whatever, it's 1.5, right? Okay, you know what? Yeah, it's 1.5, screw it. 1.5i minus, that one's 0.5 j. It's not actually 0.5, it's 0.5 and a little bit more, but come on. I agree with you. Screw it. Plus 0.25 k. That is V cross B, and F is equal to Q times V cross B. So we'd have to multiply each of these in by Q, right? And because it's a proton, we don't add in a negative sign. So if this question said electron, then each of the x, y, z components would be negativated. They would be multiplied by a negative, and therefore the direction would have flipped. But because it's a proton, it doesn't matter. So we'll say, all right, well, that force is going to be equal to 1.5 times 1.602 times 10 to the negative 19 in the I direction, minus 0.5 times 1.602 times 10 to the power of minus 19 in the J direction, plus 0.25 times 1.602 times 10 to the minus 19. You'll get really tired of writing this out in the K direction. Yay! Who is dreading doing a cross product in their exam? Me. I hate it. What you'll find is that there's some things you vibe with, there's some things you don't, right? I really vibe with any question where I don't have to do vectors. I don't mind integrals. I find integrals kind of easy and fun. I just hate vectors, right? Maybe you'll be the other way around. Maybe you really hate integrals. You really like vectors. Maybe you really like doing derivatives instead of integrals. You'll find, right? You'll find what parts of physics you like, what parts you don't like. To be quite honest, I hate every part that involves maths, but that's why I was an experimentalist, right? All I would do is just physically do the physics. All right. Who did 1A? Some of you, Yanks, you don't know. Did you do Phys 101 or whatever? No? What was the first physics course you did? What was it called? No, in university. I'm asking the American exchange students. What course was it called? Physics 1. Okay, who did Physics 1? All right, who learned about uniform circular motion in Physics 1? Slay. So, does anyone remember the two conditions? How does something undergo uniform circular motion? Well, if an object is experiencing a force, yeah, thanks. A force, no, yes, okay, good. That is constant in magnitude, and that force is perpendicular to the velocity. If those two things are true, the object will go in a circle, a uniform circle. It'll go in a circle at the same speed. if the net force, I should say net force, that's more correct, right? If the net force acting on an object is constant and that net force is always perpendicular to the velocity. Yes, Tarek? Yep. Well, this is the good part, right? So you'd think that. But in this example, the magnetic field is going into the page, right? I've drawn it as crosses. So that's what those crosses mean. The magnetic field goes into the page. It never turns into the magnetic field. It always turns along the magnetic field, like in a direction perpendicular to the magnetic field. So this object, at the moment, if we use our right-hand palm rule, we point our thumb up, we point our fingers into the page, and we would experience the force to the left, as I've drawn in the diagram. As the charge goes up, let's say it's here, right? And by the time it's here, it's turned a little, right? Because it's got a force acting to its left, so it's made it turn, right? So you take your thumb and you point it in that kind of diagonal direction now. You take your palm, so you take your fingers, and the fingers still point into the page because that's still the direction of the magnetic field. And our palm still points this way. Our palm still points along the page. One thing that's very, very useful about magnetic fields is that if the field is into the page or out of the page, one of the two, every other direction along the page is perpendicular to that. It's like how if I got a piece of paper, right? If you imagine the magnetic field going into the page like this, any direction along the paper is by definition perpendicular to the magnetic field going through the paper. And that's why for us, for magnetic fields, and not for electric, for magnetic fields, the charge does actually not eventually come into alignment with the magnetic field, but just continuously circles around. And you might ask, shouldn't it radiate energy at that point? You're like, well, of course it would. Of course it would radiate energy, right? That's what you're going to ask? Yeah, because moving charges radiate photons, but we're not dealing with that yet, right? For now, we will imagine it doesn't lose energy. Because you're right, the energy, like, is this a perpetual motion machine we have just invented? Right? Of course not. But the limiting factor here is that what happens is these moving charges will radiate electromagnetic energy, but you haven't done electromagnetic waves yet. And I don't teach it to you, I don't think. I think someone else teaches it to you. Sad. I forgot. Does anyone know who the lecturer for the second half of this course is? No? No one looked that up? Yeah, it is on Moodle. It should be, I think it's Michael. I think it's Michael. If it's Michael, okay. If it's anyone, you'll be fine. But Michael Schmidt's very good. All the lecturers are very good, for the record. I love all of you. Thank you, UNSW, for employing me. All right. So if the force is perpendicular to velocity and constant in magnitude, then any time the charge moves around in that part of the circle, the force is still the same, so it still turns. And essentially all that happens is it goes in a circle, right? It goes in a circle, and that means we can do some maths on it. We can figure out the radius of this circle. Because we, of course, remember that if an object undergoes uniform circular motion, then the net force on this object must be equal to mv squared over r, where v is the velocity, the speed, because the velocity technically changes. R is the radius of curvature, or the radius of the turn, and m is the mass of the object. So let's equate these two. E is equal to qvb, and what we're looking for is r. So first we'll delete this v and delete the squared on that v, so we get m. Really? I don't know why. Like, mv over r equals qb, so r equals mv over qb. What this means for us, the more massive the particle, or the more velocitous the particle, the greater the turn, the greater the radius of turn. Q and B are affecting the magnetic force only. So the bigger the charge, the easier it turns, or the smaller its curving radius. And the bigger the magnetic field, the smaller its curving radius. And this is very useful because you can very easily measure the charge to mass ratio of things. All right? This is how a mass spectrometer works, if you've ever used one of those, right? An ion spectrometer. Because any object with a unique charge to mass ratio will have a unique curvature, assuming a certain velocity and assuming a certain magnetic field. Question? No, just hand. Yeah. So it's a very, very useful assumption. And in fact, so useful, in fact, that you have this question on it. Where did I get this picture from? Oh, no. Maybe it's relevant to know how to do these sorts of things, right? So there's two questions we're going to go over, and then we've actually finished all the learning for this lesson. So what I will do is I will start us on the next lesson. You're taking a photo? It's not on your slides. Oh, yeah, because I uploaded I should upload the actual slides, shouldn't I, instead of just like the extra bullcrap. I put these in at the end because I was like, Tom, put more stuff in. Because I wrote those slides 2 weeks ago on Sunday, and I was tired, and I wanted to go to sleep, so I just did it. Anyway, here's an example of this is basically a mass spectrometer, all right? What it does, it has two phases. The first phase is purely electrical, okay? It accelerates the electrons to a certain velocity. And then they go in a magnetic field and they turn, okay? So we have an ion accelerator, and it has charged objects pushed through some voltage V. Then the charges move in a circular path. I want to find out if the electron goes 10 meters, so this distance is 10 meters, with a voltage of 3 volts. What's the magnetic field strength? And this is slightly more involved than you think. Only slightly. The first thing we must do for a question like this is calculate how fast the object is going. Tarek, question? Yes, that's exactly what that means. Yeah, that's one of the hidden parts of the question, right? Question? Oh, I thought you were about to say something. Oh, okay, cool, good. I also make noises sometimes. And by that I mean all the time. Yes, you're right. This means that the radius is 5 meters. And that's very good because what we do, and the way this question was written, is to bait you into using radius of 10 meters, right? Freak you out a little. But you're right, radius is 5 meters. First thing we need to figure out, how fast is it going when it enters the magnetic field? Well, yeah. So first things first, let's make sure we use, I know exactly what you mean, and that's what we're going to do. The kinetic energy of our charged object is equal to Q, the charge of that object, times big V, the voltage that that object goes through. Question? Sure, but now I'm doing this. Yeah, the thing is that because we know we've been told that it accelerates up, right? Notice I use this question, right? And the way the voltage is set up, you're exactly right. It'll accelerate backwards. So it's the other way now. Pretend this flipped over. But you're right. We should put a negative sign in there. But because we're just trying to find the speed, we're not actually caring about the direction it goes. We're just assuming it goes in the direction we want. We're just absolute valuing it for now. But I appreciate the rigor, right? Rigor is next week. Next week, all this fastidiousness is very important. This week, or unthank, it is not important, right? So this week, today, vibes. Next week, fastidious adherence to proper procedure, right? And you'll see it when you see if the equations you're using have vectors in them, like vector hats or vector symbols, you must be very fastidious with directions. If they don't, then you can probably intuit directions from the question. That's what we're going to do here. Now, this is going to be equal to 1/2 mv squared, where v here is velocity, not voltage. And now we're going to solve for v. So v is equal to 2 qv over m square rooted. Okay? Now we check. Do we know all of those numbers? We know v. We got told it. It was 3. We know M, it's an electron. We know Q, it's an electron. Hang on, I'm going to annoy these students. 你们在做什么？你可能过来啊？你喜欢学物理吗？No? Okay, 没问题啊。拜拜。Oh, they got freaked out. I'm sorry. I just like yelling. I said, what are you doing?
Did you speak Japanese?
That was Chinese, bro. That was the best part is like the complete relaxed pose at which you said that. How do you say that in Japanese? I don't know. I'm not gonna. My Japanese accent is terrible. No, that's it. Yeah. Anyway, whatever. Anyway, we got V. We got the velocity. All right. So now we're gonna find. We want to find magnetic field strength, right? Right? Yep. And we remember that R. Do we remember what R was equal to? mv over qb. Yeah, that's the height we want. Let's go. Well, yeah, anyway, whatever. All right, so now we do this. Now we rearrange to find B. Right, so we got B is equal to mv over qr. Okay. And we have all of those except V, but V is this. So we just put those together. We have M over QR, this is what B is equal to, times this big horrifying schmozzle. Right? Now, then we put some stuff in, we go, well, actually that means that this is equal to 1 over R times, there's a reason I didn't take the square root out, right? Times the square root of 2mv over q. Right? Do you see what we did there? See how you put the m in the square root becomes m squared and then it cancels out with the other m? Wow, slay. And then you evaluate it. Right? So that's 1 over 5 times more people. The square root of 2 times the mass of an electron, you know, times the voltage over q. Now what I want you to realize, right, is this final equation. I'm not going to bother to evaluate it because I'm too lazy, right? Right? But the magnetic field is equal to 1 over R, all this stuff. Right? If you swapped B and R, so if you say solved for R is unique if M over Q is unique. Right? If M over Q is unique, then R is unique. And that means you can use one of these things. If you measure the radius, you can figure out what the charge to mass ratio of the thing is. But what you cannot do is figure out the charge or the mass. And this was the entire problem back in the olden days of this machine. This doodad we have here, right, is how we discovered the electron. And the discovery of the electron was done not in the isolation of its charge or its mass, but in the ratio of its charge to mass. Because a very common apparatus that you will see is a force balance like this, where there will be a magnetic field applied that deflects the beam in one direction. I'll put it at the back, actually. So there'll be a magnetic field applied that deflects the beam in one direction, and then there will be an electric field applied that corrects it and makes the net change 0. Okay? So let me turn this on. Don't die. I'm going to slowly up the voltage. Is it connected? It's connected. All right, let's go. Oh, just because of the thing that glows. It's just a glowy thing that glows blue. The electrons aren't actually blue. The electrons don't have a color. Now, here's hoping I don't break this. So we have like an electric field deflecting it one way, and then the intent is we bring in the magnetic field, deflect it the other way. Okay? And there was a very, very old experiment like this done back in the olden days to balance the electric and magnetic fields and therefore calculate the charge to mass ratio of our object. So let's replicate that experiment because it's relevant. And it's also our last slide, I think. Yeah, it's our last slide. So what's happening here, and I'll let you come and play with it under supervision if you want, is we have an electric field causing a deflection because F equals QE. We have a magnetic field, and notice how I put the magnetic field not in the same direction as the electric field, but perpendicular to it, right? We have a magnetic field that at some point causes an exact opposite deflection, QVB. And what we will do is we will equate the two, right? We're going to equate QE equals QVB. Now, it doesn't actually matter. You know what does matter? Where I put the pen. There. Do you know, by the way, these gas taps, we found out recently, do not have a safety valve, and they could have just been leaking the entire time. Yeah. So it's a miracle no one died. Like, legitimately, there could have been a gas leak for months, years, decades. This building is also full of asbestos. No. No, no. You would be surprised at how dodged things are here. You know the first year lab? You know those tables? Those tables are the ones that give you silicosis, the cancer. Yeah.
Oh, yeah.
So do not eat the tables. Do not vaporize and inhale the tables. Anyway. Yeah, don't vape the table.
We're not supposed to eat the silver ink. Now we're not supposed to eat the tables?
Yeah, don't eat the silver ink, please.
Aren't you going to tell us we're cutting the computers? That'll be the day, huh?
So the common case that you see in these sorts of questions is you have an electric field that is applied, right, along one direction, and then you have a magnetic field that is applied in a perpendicular direction, so usually into the page, right? This is supposed to be a GIF, by the way, so it doesn't work, right? But what you get is a magnetic field that applies a force. We could call it the magnetic force on this charge. And we get another that gives us the electric force, right? And the idea is that you try and balance the two. And if you try and balance these two, what do you get, right? Well, we get QVB equals QE, and therefore V equals B over E. E over B. I'm dumb, right? V equals E over B. And why is that useful, right? Well, I want you to imagine you're trying to do this experiment, right? You're trying to figure out the charge to mass ratio of these things, and you do not know their charge. So if you were to try and find the velocity of these charges using our previous method, QV equals half mv squared, you don't know Q and you don't know M. So you couldn't calculate it. But what you do know is that for the electric field that balances the magnetic field, you can measure the electric field, you can measure the magnetic field because we had definitions for them back then. You know that this is true. And the idea is, if there's no electric field and you keep the magnetic field the same, it curves in a circular arc. So what you do is you measure the radius of the curvature. It's what Thomson did back in the day. They had their electrons shooting straight, they deflected them, and they measured exactly how far they deflected. Then they turned on the electric field and got it the wrong way. Okay, so they deflected them to find out exactly how far they deflected. Then they turned on the electric field and increased the electric field until it balanced. Once it balanced, they measured that electric field, they measured that magnetic field, and they got this. The velocity of those charges must be the ratio of those two fields. And then they went, well, I also remember that R equals, what was it? MV over QB. And so we just put that in. We go, well, the radius of curvature is now M over Q E over B squared. And we now have we can measure the radius of curvature. We can look at where it goes. We measure E and B because we define those things. Back in the day, in the 1800s, when people were making electric and magnetic fields, we could define E, we could define B. And now you have a mechanism purely by doing this two-stage process of deflecting it and then balancing it. I see your question. I'll answer in a second. You are able to find the charge to mass ratio, or technically the mass to charge ratio. And this is how we... Okay, question first.
Okay, so I'm making the assumption that they're accelerating throughout the tube.
No, we should assume that they do not accelerate throughout the tube. So in the ideal case, the acceleration happens here only, right? But that is a good point, right? So in this case, we're assuming they get accelerated here. Yeah, there we go. We're assuming they get accelerated there, then they're going at a constant velocity, right? But that is a very good point. If it wasn't a constant velocity, this wouldn't work, right? This nice, smooth assumption. And so this was, by the way, how the electron was first discovered. Because you can find the charge to mass ratio of anything, right? And the charge to mass ratio of the electron is dramatically larger than anything else, right? What is the next largest charge to mass ratio, do you think, after the electron? Q over M, not M over Q. The proton. The proton has the same charge as the electron and a mass of 10 to the 16 times more? No, not 16. What's the mass of a proton? Oh, it's 24 or something, right? 27. All right, so that's 10,000 times, right? So a proton has the same charge and 10,000 times more mass, which means the charge to mass ratio of the electron is so much greater than the proton and therefore everything else that it had to be its own particle. That was how we figured out, like any of us contributed anything, but that is how it was figured out that the electron was its own particle, because the charge to mass ratio of this thing was off the frickin' charts. So that is our introduction to magnetism. Now that's our first little lecture. We only have 10 minutes. All right, I'm going to foreshadow. Oh, sorry, we'll escape. No, we'll keep the incantations, good. And I'm just going to foreshadow something. So we'll go back to my top page, all right? And I want to foreshadow, I want the slides to work. There we go. I want to foreshadow a thing. So, remember what we learned? New magnet stuff, which is what we're doing next week. And we also learned capacitance stuff. We won't deal with capacitance stuff again. But what I want you to think. Oh, it's red again. I hate red. All right. Blue. Blue. All right. Imagine a wire. And imagine, for the sake of argument, that current in this wire is the flow of positive charges along the wire. When you place a magnetic field on this wire, those charges are each going to experience a force, right? And importantly, you have two ways of thinking about it, and this is what is especially confusing. The first one is the one you learn in high school. You treat the current as its own distinct entity, right? And you say, well, the force on the current is actually the length of the wire times the magnetic field times the B, times I times the B field. Hang on. Fellas, what's up?
Hi, I'll be doing a lecture later.
Oh, you can come in now if you want.
Let's come in.
Come on in. We're just doing dumb shit.
Sounds good.
Yeah, I know, it sounds good. Right. So the common case that you're used to is treating the current as its own quantity, right? But in reality, of course, each of these individual charges is individually experiencing this force. And let's say that the force they're experiencing is upwards, right? Well, in reality, what should happen is you should start to get an accumulation of positive charges at the top of this wire and an accumulation of negative charges at the bottom of this wire. This thing is called the Hall effect. And it necessitates thinking about current in a different way. when we consider current in the Hall effect, we are considering J, the current density, which is the flow of individual charge carriers, okay? So for next week, if you were to look up what current density is, right? It is just current divided by cross-sectional area, right? But it is a distinct concept to current, and current density shows up in a lot of equations, and current shows up in the other lot of equations. It's cursed. You have my apologies. But you'll need to know the two different things. You already know what current is, so I'm not bothering to explain it. But current density is the total current, but how dense is it in the wire? Are the charges, is there a lot of charges? Are they moving fast? Are they moving slow? This sort of thing is actually important, right? When you consider things like the Hall effect, when you consider the charges as individuals. If you consider the charges as a mass as a whole, then it's just current. But if you consider each individual charge as its own distinct entity, you need to know what the current density is. And that's the thing I want to foreshadow for next week. So thank you all so much for coming to lecture. And we're done for the week. Yay! We did it. All right, we'll save. This is the second lecture in a row that actually finishes on time. Isn't that great? I am so shocked. Oh, the next two lectures oh no. The next two lectures we're back. We're back. Sorry? Oh yeah. Next lesson, we're back. It's integral time. If you missed integrals, oh, they're so back. They're so back. It's integrating things with cross products in it. I hate it. We're doing line integrals, we're doing path integrals, we're doing circulating path integrals, we're doing integrals of things that have cross products of things, we're doing integrals that involve current density and integrals that involve current. It's goated. We're all going to die. Bye. What? There is no way out. The way is shut. See ya. Have a good one. No, the way is shut. There's no way.
Nice having another Friday. Good luck.